Welcome to the public exam review on Chapter 8, dealing with logarithmic functions. In this session, we will be solving logarithmic equations. Here we will focus on solving a logarithmic equation and verifying the solution. We will explain why a value obtained in solving a logarithmic equation may be extraneous. We will use the laws of logarithms throughout this presentation. Recall that the product law of logarithms states that the log of a product is equal to the sum of two logs, keeping the same base. The quotient law of logarithms states that the log of a quotient is equal to the difference of two logs, all with the same base of c. And the power law of logarithms states that the log of m raised to the power of p to base c is equal to m times the log of m to base c. We will also use these two properties of logarithms as well. If the log of L is equal to the log of R, maintaining the same base of c on both sides of the equation, then we can conclude that L is equal to R. Conversely, if L is equal to R, then we can take the log of both sides of the equation to get the log of L to base c is equal to the log of R to base c. Let's look at some examples. Here we will solve each of the following logarithmic equations. We have the log of x to base 3 plus the log of x minus 2 to base 3 is equal to 1. Notice on the left side of the equation, we have the sum of two logarithms. So we can rewrite that as the log of a product. X multiplied by x minus 2 to the base of 3 is equal to 1. In order to remove the word log, we need to convert that equation in logarithmic form to exponential form. So we have 3 raised to the power of 1 is equal to x multiplied by x minus 2. 3 to the power of 1 is equal to 3. And then we have x squared minus 2x on the right-hand side. This results in x squared minus 2x minus 3 is equal to 0. This equation can be factored as x minus 3 multiplied by x plus 1 is equal to 0. X minus 3 equals 0 when x is equal to 3. X plus 1 equals 0 when x is equal to a negative 1. Now we need to check for extraneous roots. Extraneous roots are solutions that do not work when substituted back into the original equation. So for example, when x is equal to 3, we are taking the log of 3 plus the log of 1. We are able to do that because you could take the log of a positive number. However, when x is equal to a negative 1, you cannot take the log of 0 or the log of a negative number. Therefore, we are forced to reject x equals a negative 1. It is considered to be an extraneous solution. So in this example, the only solution is x equals 3. Next, we have the log of 4x minus 7 to base 3 minus the log of x to base 3 is equal to 1. Notice that we are taking the difference of two logs on the left side of the equation. This can be rewritten as the log of a quotient, namely 4x minus 7 divided by x to the base of 3 is equal to 1. Again, we need to convert this to exponential form, so we have 3 raised to the power of 1 is equal to 4x minus 7 divided by x. Cross multiplying, we get 4x minus 7 is equal to 3x. 4x minus 3x will equal 7, so we have x equals 7 as our final answer. We still need to check for extraneous roots. So when x is equal to 7, we are actually taking the log of 4 times 7 is 28. 28 minus 7, we are taking the log of 21. And here it's the log of 7. So this is not an extraneous root, so x equals 7 is an acceptable solution. In the third example, we have 1/3 in front of the log of 27. So we can rewrite that using the power law of logarithms as 27 raised to the power of 1/3 to the base of 3 plus the log of x to base 3 is equal to, and we could change, well, we can leave it as 4 to the 1/2 right now. 27 to the 1/3. Notice that we have a fractional exponent here, so we could convert that to a radical. That would be equal to the cube root of 27 to base 3 plus the log of x to base 3, and similarly, 4 to the 1/2 can be rewritten as the square root of 4. So we have the cube root of 27 is equal to 3 to a base of 3 plus the log of x to base 3, and the square root of 4 is equal to 2. On the left side, we have the sum of two logs, which can be rewritten as the log of a product. 3 times x to base 3 is equal to 2. Converting to exponential form, we have 3 squared is equal to 3x, so 3x is equal to 9, therefore x is equal to 3. Again, when you check for extraneous roots, we are allowed to take the log of 3, so that would not be an extraneous root, and x equals 3 is an acceptable solution. Let's look at some potential questions that could be asked on the public exam. This will be an example of a typical multiple choice question. I chose this example because if you notice, the bases here are different. So here you have a base of x, here you have a base of 3. So that means directly that you cannot use the law of logarithms to begin this solution. So we have the log of 2x plus 8 to base x is equal to the log of 9 to base 3. Notice that the number 9 can be rewritten with a base of 3. So we have the log of 2x plus 8 to base x is equal to the log of 9, which is rewritten as 3 squared, to the base of 3. Recall the property of logs. The log of c to the power of k to base c is equal to the exponent k. So we will apply that property of logs to the right-hand side of this equation. So we have the log of 2x plus 8 to the base of x is equal to 2. Now we will take this equation and convert it to exponential form. So we have x squared is equal to 2x plus 8. Bringing all terms to one side, x squared minus 2x minus 8 is equal to 0. This can be factored as x minus 4 times x plus 2 is equal to 0. Continuing, we have x minus 4 is equal to 0 when x is equal to 4. As well, x plus 2 is equal to 0 when x is equal to a negative 2. It is important to remember that the base of a logarithm cannot be negative. Therefore, we have to reject x equals a negative 2 as a possible solution. We have to reject a negative 2 because we can't have a negative base. Therefore, your only solution in this example is x equals 4. So this answer corresponds with D as the multiple choice item. In example 2, we are asked to solve for x. We have 2 times the log of x to base 2 plus the log of 4 to base 2 is equal to the log of 64 to base 2. There are several ways to attempt this question. One thing I would like you to notice is that when the base of the logarithm, when the power can be rewritten with the same base as the log, we can use that rule property for logs again. So we can put the 2 in the front of the, we can say the log of x squared to base 2 using the power law of logarithms. But we can rewrite the number 4 as 2 squared to base 2. And we can rewrite 64 as 2 to the power of 6 to base 2. Then we have the log of x squared to base 2 plus 2 is equal to 6. So then we have the log of x squared to base 2 is equal to 6 minus 2, which is 4. Converting to exponential form, we have 2 raised to the power of 4 is equal to x squared. Therefore, we have x squared is equal to 16. So x is equal to plus or minus the square root of 16. So we have x is equal to 4, or we can have x is equal to a negative 4. When you look at the original equation, notice that you would be taking the log of a negative 4. This is not possible, so we have to reject x equals a negative 4 as a possible solution. And your only answer in this case would correspond with C as your multiple choice item. In example 3, we are asked to solve for x. We have the log of 5x plus 2 to base 5 is equal to 1/2 times the log of 49 to base 5 plus the log of 16 to base 5. So let's begin by using our power law of logarithms. So we have the log of 5x plus 2 to the base of 5 is equal to the log of 49 raised to the power of 1/2 to base 5 plus the log of 16 to the base of 5. Then we can take the square root of 49. So we have the log of 5x plus 2 to base 5 is equal to the log of 49 to the 1/2 can be rewritten as the square root of 49. And we know that that answer is equal to 7. So then we have the log of 5x plus 2 to the base of 5 is equal to the log of 7 to base 5 plus the log of 16 to base 5. When you look at this example, we see that we have the sum of 2 logs on the right-hand side of this equation. So we can rewrite that as a log of a product. So we have the log of 5x plus 2 to base 5 on the left, and 7 multiplied by 16 is equal to 112 on the right-hand side with a base of 5. Remember that if the log of L is equal to the log of M to base 5, then L must equal M. So we can now conclude that 5x plus 2 is equal to 112. Solving for x, we can subtract 2 from both sides of the equation, so 5x is equal to 110, and dividing both sides by 5, we are left with x equals 22 as our final solution. And this answer corresponds with B in the multiple choice items. In example 4, this was a long answer question that was taken from a previous public exam. Here we have the log of x minus 5 to base 9 plus the log of x plus 3 to base 9 is equal to 1. On the left-hand side, notice that we have the sum of 2 logs, so that can be rewritten as the log of a product. The log of x minus 5 multiplied by x plus 3 to the base of 9 is equal to 1. Converting to exponential form, we have 9 raised to the power of 1 is equal to x minus 5 times x plus 3. So 9 is equal to, that will be x squared minus 2x minus 15. So we have x squared minus 2x minus 15 minus 9 is equal to 0. X squared minus 2x minus 24 equals 0, and that can be factored as x minus 6 times x plus 4 is equal to 0. Then we know that x minus 6 is equal to 0 when x is equal to 6, and x plus 4 equals 0 when x is equal to a negative 4. We also need to check for extraneous roots by substituting these values for x back into the original equation. So when x is equal to 6, we would be taking the log of 1 in the first term, and in the second term we would be taking the log of 9. When x is equal to a negative 4, here we would be taking the log of a negative 9, and here we would be taking the log of a negative 1. It is important to remember that you cannot take the log of 0 or the log of a negative number, so it is essential that we reject x equals a negative 4, and our only solution in this example is x equals 6. In this example, we again are asked to solve for x. We have the log of x plus 7 to base 4 minus the log of x squared plus 3x to base 4 is equal to 1/2. Notice on the left-hand side that we are looking at the difference of two logs. So we can rewrite that as a log of a quotient, namely x plus 7 divided by x squared plus 3x. And that's all to the base of 4 is equal to 1/2. Now we need to convert to exponential form. So then we have 4 raised to the power of 1/2 is equal to x plus 7 divided by x squared plus 3x. 4 to the power of 1/2 can be rewritten as a radical, which is equal to the square root of 4 is equal to x plus 7 divided by x squared plus 3x. The square root of 4 is equal to 2. So we have 2 multiplied by x squared plus 3x is equal to x plus 7. So that results in, I'll just go up to the other side to finish the solution. So we have 2x squared plus 6x, bring all terms to one side and let it equal 0. So we have 2x squared plus 5x minus 7 is equal to 0. In this case, we can say 2 multiplied by a negative 7 is a negative 14. And the factors of a negative 14 that have a sum of a positive 5 would be 7 multiplied by a negative 2. So now we can use decomposition. We could say 2x squared plus 7x minus 2x minus 7 is equal to 0. Removing the greatest common factor from the first two terms, we have x outside of 2x plus 7, minus 1 is the greatest common factor outside of the last two terms, so it's minus 1 outside of 2x plus 7 to equal 0. So we have the factors as 2x plus 7 multiplied by x minus 1 is equal to 0. At this stage, you should use your FOIL method to check and make sure that your factors are correct. So we have 2x times x is 2x squared. Your outside terms, the product is a negative 2x, plus the product of your inside terms, a negative 2x plus 7x is a plus 5x, and your last terms, the product is a negative 7. So the factors here are correct. So then we have 2x plus 7 is equal to 0, 2x is equal to a negative 7, so x is equal to a negative 7 over 2, which we know is equal to a negative 3.5. As well, x minus 1 equals 0 when x is equal to 1. We need to check for extraneous solutions. So when x is a negative 3.5, a negative 3.5 plus 7 would give us a positive 3.5, so we could take the log of a positive number. And similarly, when you substitute in a negative 3.5 and square it and add 3x, you will still get a positive number. So in this case, x equals a negative 3.5 is an acceptable solution. When x is equal to 1, here you would be taking the log of 8, that's okay. And here you would be taking the log of 4, and that's still okay. So in this case, we have two solutions. X equals a negative 3.5 and x equals 1. Let's look at one more example. Here we are asked to solve for x. You have 2 raised to the power of x plus 4 multiplied by 1/4 raised to the power of x minus 1 is equal to 3. Notice on the left-hand side that we can express both of these terms with a base of 2. So we could say 2 raised to the power of x plus 4 multiplied by 1/4 is the same as 1 over 2 squared. Still raised to the power of x minus 1 is equal to 3. So then on the left-hand side, we have 2 to the power of x plus 4 multiplied by 1 over 2 squared is the same as 2 to the negative 2. Raised to the power of x minus 1 is equal to 3. So then what we have, using a power of a power, we have 2 to the x plus 4 multiplied by 2 to the power of negative 2x plus 2. This is a power of a power where we multiply the exponents. And then the right-hand side is equal to 3. The left-hand side can then be simplified. If you multiply powers with the same base, you can simply add the exponents. So x minus 2x is just a negative x, and 4 plus 2 is 6. So we have 2 to the power of negative x plus 6 is equal to 3. Notice here that we have two powers that are equal, but however the bases here are different. So the only way in which we can algebraically determine the solution here is to take the log of both sides of the equation. So we have the log of 2 raised to the power of negative x plus 6 is equal to the log of 3. And now we can use our power law of logarithms to complete the solution. So we could take the exponent. We could take the exponent of negative x plus 6, and we can move it in front of the log of 2 to equal the log of 3. And now what we're going to do is we're going to divide both sides of this equation by the log of 2. That results in a negative x plus 6 is approximately equal to, when you divide the log of 3 by the log of 2 on your calculator, you will get 1.5850. Then we can have 6 minus 1.5850 will approximately equal x. Therefore, x is equal to 4.4150. And that would be our final answer. As a summary then, when solving a logarithmic equation algebraically, we can start by applying the laws of logarithms to express one side or both sides of the equation as a single logarithm. Some useful properties are listed below, where c, l, and r are greater than 0 and c cannot equal 1. So notice that c is the base to your logarithm. So c has to be greater than 0 and c cannot equal 1. So if the log of L is equal to the log of R with the same base of c, then L is equal to R. Similarly, if L is equal to R, then we can take the log of both sides of the equation. So the log of L to base c will equal the log of R to base c. It is important to remember that the logarithm of 0 or a negative number is undefined. I would like to highlight that for you because it is used frequently when solving logarithmic equations. And to identify whether a root is extraneous, substitute the root into the original equation and check whether all of the logarithms are defined. You can solve an exponential equation algebraically by taking the logarithm of both sides of the equation. We did this in the very last example. If L is equal to R, then the log of L to base c is equal to the log of R to base c, where c, L, and R are greater than 0 and c cannot equal 1. Then we will apply the power law for logarithms to solve for the unknown. Thank you for your time and your attention. If you have any questions related to the content of this presentation, please post them in the question forum and we will be happy to answer them for you. Good luck with your review.